Hello everyone. So a couple of days ago, we found out that simple harmonic motion, right, a vibratory or oscillatory motion, a special kind, right, is or can be thought of as the projection of uniform circular motion onto an axis. And so combining uniform circular motion and rotational motion into simple harmonic motion, we came up with a position as a function of time equation for simple harmonic motion of x of m cosine of omega t plus phi. This is where x sub t is the position of the simple harmonic oscillator as a function of time. X sub m is the amplitude, maximum displacement from the equilibrium position. Omega is the angular frequency, 2 pi over the period, or 2 pi times the linear frequency. And t is just generic time. Phi is the phase constant, otherwise known as the phase angle. This is kind of the starting position, right, of the simple harmonic oscillator. Zero phase angle is when you are at the positive amplitude, okay, wherever that is. So for this mass on the end of a spring, it would be when you're at the highest point. This mass on the end of a spring, it would be when you're furthest to the right. Okay, that would be a phase angle of 0. And then yesterday we started to look at, well, if this is the position, right, what does the velocity look like? What does the acceleration look like? What does the force as a function of time look like for a simple harmonic oscillator? And we looked at different graphs of a mass on the end of a spring, right, as our paradigm object, and kind of compared them one to one another. Oh, and this is a positive maximum. What's this one? Right? What's the velocity? What's the acceleration? So now it's time to theoretically look at why we got what we saw in the lab yesterday. Right? Why did the velocity function and the acceleration functions and the force function look the way they did? So this is going to take a little bit of calculus. All right? And if this calculus is a little on the high end for you, that's okay. It's not something they're going to ask you to derive on a test. Right? They would expect you to recognize the equations we end up with, right? But you won't have to get from one to the other kind of thing. So, you might be able to piece this together. Now, if you can do the calculus, the advantage is all you need is this function, and you can get the other two, right? So, if we've got a position function as a function of time, right, the velocity of a simple harmonic oscillator would simply be the derivative of the position with respect to time. That means the derivative of x sub m cosine of omega t plus phi. Okay? Now, this is the derivative of a cosine function, but it's also the derivative of a cosine function with an expression inside. If you've done enough calc, you know that what we have to do is we take the derivative of what's inside times the derivative of the cosine function. And the x sub m is a constant and just rides along, right, for the ride. So, let's look at the derivative of this expression omega t plus phi. If we take the derivative of omega t with respect to t, right, that's just omega. Right, omega is a constant. Phi is the phase angle or the phase constant, the starting position in a simple harmonic motion. It's a constant, right? So the derivative of a constant is 0. There is no rate of change. So the derivative of omega t plus phi is omega. What's the derivative of a cosine? Negative sine. Right? So the derivative of x of m cosine of omega t plus phi is negative omega x of m sine of omega t plus phi. Which means the velocity function is a sine function. You might remember that from yesterday. Right? When the position was a maximum, the velocity was 0. When the position was 0, the equilibrium position, the velocity was a maximum. Right? Well, isn't that the way cosine and sine work? Right? 0, when a cosine is 0, the sine is 1. When cosine is 1 or negative 1, the sine is 0. Right? That's the way these two functions work. So it kind of makes sense that it's a sine. Now, this expression out in front is important, right? Because the velocity function is going to vary as the sine of omega t plus phi varies, right? But the sine function always oscillates between -1, and +1. So a maximum sign is going to be a -1 or a +1. Well, -1 or +1 then times this give us our maximum velocity. You with me there? So kind of like this is the position amplitude. This is the velocity amplitude. V with a subscript of little m. Okay, this is the velocity amplitude. This is the maximum velocity. Positive or negative depending on if it's going up, down, right, or left, right? Depending on what kind of oscillator it is. Okay. Now, this is not something that the AP curriculum expects you to know. It's not part of the AP curriculum, but it can come in really handy if you remember it. Okay. For example, they might ask you a question like, what's the maximum velocity of this mass on a spring? Well, if you know the velocity amplitude, boom, right? You plug stuff in, you find it. Whereas the AP people may be expecting you to do some sort of conservation of energy problem, which would be much more involved than just using this equation. Right? So it's a handy thing to remember. Okay? So this is the velocity, and notice how it matches with what we saw yesterday. Well, what about the acceleration? Well, of course, if we've got a velocity function, right, we take the derivative of it and we get the acceleration. So this is the derivative of -omega x of m sine of omega t plus phi. Well, same kind of process. You've got to take the derivative of what's inside times the derivative of the sine function. Well, the derivative of what's inside is, again, another omega. So another omega is going to get put outside. That would be omega squared then. The derivative of a sine is a cosine. Now be careful. Derivative of cosine is negative sine. Derivative of sine is just a cosine. Okay, so that negative is going to stay there. So we get negative omega squared x of m cosine of omega t plus phi. Okay, so notice this negative sign in here. Right? So notice that that means that the acceleration is in the opposite direction of the position all the time. Now, if you think about that, I hope it makes sense, because it's caused by a restoring force. So if the position is positive, the acceleration and the force have to act the other direction to push it back towards equilibrium. Otherwise, you don't oscillate. Right? You have to have a restoring force all the time. Okay, so that's why that negative sign has to be in there. Now again, the cosine oscillates between -1 and 1, right, as maximums, negative maximum and positive maximum. So notice when the cosine is -1 or 1, the acceleration is positive or negative omega squared x of m. So this becomes the acceleration amplitude. And again, handy to know, right, because maybe they really want you to do some sort of force analysis to figure out the maximum acceleration. But if you know this equation, pull this equation out and use it, right, and you might be able to find it easier. Again, this is not part of the AP curriculum, but it is a handy thing to know. Now, I want you to check out this acceleration function, though. Do you see something inside of it? Inside of this acceleration function is x of m cosine of omega t plus phi. But isn't that x? Right? X is a function, position is a function of time, was x of m cosine of omega t plus phi. So if we plug that in, the acceleration as a function of time is really negative omega squared x. Now be careful, this x is a loaded x. This x means x of m cosine of omega t plus phi. This is the thing that varies as time goes on, right? But this is the acceleration function that we're going to use in some of the proofs we're going to do, some of the derivations we're going to do on particular simple harmonic oscillators, right? This is going to come in handy to know, right? So this is the acceleration function. Really, it's this big thing, right? But we can shorten it down to negative omega squared x. All right? Now, if that's the position, velocity, and now acceleration function, what about the force that results in simple harmonic motion? Well, we know according to Newton's second law that net force is mass times acceleration. And we now know that the acceleration of a simple harmonic oscillator is negative omega squared x of t right, where x sub t is x sub m cosine of omega t plus phi. Plug this in for A, and we get a force function. Now be careful, it's negative m omega squared, right, times x. But this again is a loaded x. This is really x as a function of time, which for a simple harmonic oscillator is x sub m cosine of omega t plus phi. So the force is going to change, right? Force is going to change when the position changes as a function of time. Now notice though, here is our original definition of simple harmonic motion, but derived theoretically. If you remember, our original definition was something is moving in simple harmonic motion if the force acting on it is proportional to the position, but opposite in sign. Right? And that's what this equation says. M and omega are constants, so the force is proportional to position, but in the opposite direction. Now granted, this position is this, okay, so it's changing. Realize that this is only like the second time that we've dealt with something, besides doing calculus a lot, of a non-constant force, right? Our first one that we've used are springs, which we're really using here too. But simple harmonic oscillators also have non-constant forces. They're just more complex. So notice, the force is the opposite of the position. So you might remember, graphically, the position function and the force function looked very similar, except the force function was flipped over. Right? It was inverted. When the position was a positive max, the force was a negative max. When the position was zero, so was the force. Right? Zero position means zero acceleration, means zero force. Right? So all these things work together. So hopefully, with the lab you did yesterday, right, and then seeing the theoretical, and it helps you kind of pull apart what's going on at different points in a simple harmonic motion. Right? So you kind of have an idea of the maxes, the positive maxes, the negative maxes, and the zeros, right, and where those are for various values.